Welcome everyone to a series of teachings that we push out in computer science. Like I said in the earlier lectures, this series of teachings would come in handy for anyone in computer science, software engineering, information science, a lover of computer science. But basically, our target audience are undergraduate students of University of Calabar and Arthur Jarvis University, where I have the privilege of teaching them compiler construction. So please welcome to this class. We'd like to ask you to please like our videos, subscribe, and then hit the notification, bell, so that whenever we push out more videos, you could actually, have them handy. Welcome. So this is the concluding part of the lesson that we started in compiler construction. Remember, we looked at the phases of compilation where we saw, the compilation phases broken down into several phases, from the lexical analysis phase to the syntax analysis phase, to the semantic analysis phase. Now, in this lesson, we're going to take the concluding phases, which include the intermediate code generation, code optimization, code generation, and then all of these phases actually work in sync with the symbol table management and the error handler. So we're going to look at all of this in the very short time that we have. Now, intermediate code, as the name suggests, is intermediate. So we are not looking at any specific target computer system, to represent it in any particular machine code yet. Is an intermediate representation. It's like it's sitting between the high level language and the low level machine language that we actually intend to arrive at the end. Remember that the reason for compilation is that we actually want to move from our target language to from our source language to our target language, which is actually machine code. So we have to represent this in several forms. There are several ways of representing intermediate code. Number one, we have the abstract syntax tree, we have the polished notation, and we have the three address notation. We'll look at them briefly, not in so much details, because this will actually come up when we're taking intermediate code generation as a specific subtopic in compiler construction. All right, so this is an example of an abstract syntax tree. This syntax tree, like every tree, always has a node, and then you have leaves. Ironically, in computer science, our trees are always upside down. So you have the leaves down and the node up. So this is the node. This is an assignment statement. You have the identifier on the other side, the X, and then you have the expression that you actually want to equate to what you have on the left-hand side. So this forms the node of this tree. And then on every other node, subnodes that we have of this tree, you see the operators. So you see the division operator here. That is this division operator here. You see the addition operator here. Beautiful. That is adding, A and what we have on this side. And then, of course, you see all the operators. So on the note, on the subnodes, you have all the operators. And then at the leaves, you have what? The operand. So you see X here, you see your A here, you see your B here, you see your C here. So at the end, we're saying that X equals to A plus B. Of course, you have your parentheses multiplying B and C together. And then you have, everything on this other side is divided by, A, and then you have minus B times C. So that is an abstract syntax tree, and it is one form of intermediate code representation or generation. Now, and apart from the the abstract syntax tree, we also have the polished notation. And the polished notation is made up of three variants. You have the infix notation, you have the postfix notation, and you have the prefix notation. Now, these are self-explanatory, just like their names are. Talking about infix, you have the operator in between your operands. So here, what are your operands? Your operands, you have your A, you have your B, and then you have your operator. Beautiful. So in this case, you have the operator in between A and B. In the case of the postfix notation, you have the operator appearing at the end of the operand. So you have your A and B, and then you have your plus sign. With the prefix, you have the operator preceding A and B. Now we see a typical example of a Polish representation here. Now, in this case, of course, you have your A and B, A minus B. So you have that A and B here, and then the minus sign is at the end. Okay, so you see that minus sign represented at the end. This is an example of what? A postfix, notation. Of course, you have your C and D here, C plus D, so C and D, and then you have your addition sign at the end of that. Beautiful. And then you have your A and B, and then after that you have your minus sign, but because this addition adds this, ones in parentheses and this ones in parentheses, you have that addition sign appearing at the end. So that's a simple illustration of your Polish notation. Now, the third form of representing your intermediate code is what we call the 3 address code. 3 because you can take a maximum of 3 operators, 3 operands, sorry, 1, 2, and 3. You can have less, but the maximum is 3. So you have 1 here, you have the second one here, and you have the third one here. Now, we're going to see the representation of this on the next slide. Okay, so we see that. Now, please note, like we said, the rule is that you have the address statement and it's of the form X equals to Y and an operator and Z. Beautiful. Here, X, Y, and Z will have what? Address or memory location. So you have to represent them, using temporary variables. So we see an example here of A plus B times C plus D. Now, remember that, we also follow the precedence. Remember that multiplication and division take a higher precedence, over addition and subtraction. Remember that. Beautiful. So we start with this because it takes a higher precedence. So B times C is represented, temporarily in T1. So that goes to T1. But we have to continue with what we have. So how does T1 relate with the other things that we have? This is now T1. So T1 has to be added to A. So T1, A plus T1 is now represented in T2. Beautiful. And then, of course, you have to solve the entirety of this. So all of this is represented in T2, remember. So now T2 plus D is what we now have in T3. Don't forget that T1, T2, and T3 are temporary variables. Beautiful. Now, at the end of, intermediate code generation, where we have seen 3 different ways that can be done, we actually have to think of optimizing code. Someone says that, I think his name is Shah, he wrote a book, Compiler Construction and Advanced Course. He actually says that, calling this code optimization is a misnomer. Why? Because it's an undecidable problem. It cannot be solved by an algorithm on a computer. But be that as it may, we always attempt to optimize. In optimization, remember, you're either maximizing or you're minimizing, remember, and then you always have constraints. I mean, that's in operations research, but optimization is optimization anywhere. So dealing with code, you want to do what? Optimize your code. You want to be able to make your code faster. You want to be able to make your code reduced in the number of, program steps. Beautiful. And you want to use less memory. That's what code optimization is about. So ultimately, you want to produce code that is faster. Beautiful. Now, we have 2 forms of code optimization, just like we saw in the very first lesson that we had in this compiler construction. So we have machine-dependent code optimization. Of course, when you're talking about machine-dependent, you're bothered about, you're concerned about what your target machine code is. So at that point, you're dealing with register allocation, you're dealing with, special mention of instruction sequences. Beautiful. But when you're talking about machine-independent code optimization, you're not really bothered about what your target representation is. So in this case, you're just trying program transformations. You want to remove dead code. You want to, be able to reduce code as much as you can. There are several techniques to this that we'll talk about when we're actually dealing with machine-independent code optimization. But you should also always know that you're trying to get code that is faster, code that is shorter, and code that consumes less power and less memory. So we see an illustration of this. Remember this code, okay? So we had, 4 lines of code, representing what we actually had in this, but we try to reduce this to 2. So instead of converting, this integer into floats, why don't we just put, the float points representation, which is 0.60.0, sorry. So that is represented here. And remember that we are trying to multiply that with what we have in ID3. So we just carry that out. So we reduce this 2, steps into 1 step. And then after that, we reduce the other remaining 2 steps into 1 step, and our result is stored in ID1. So that you're trying to make your code shorter, you're trying to make it faster, you're trying to occupy less space in memory or memory-wise. Beautiful. Now, the last phase in all of this is code generation. Remember that your ultimate purpose, your ultimate aim in compiler construction or in compilation, the compilation process, is that you want to generate code. You want to get your target code. So how do we go about this? Now, this is a representation of the code that we had explained earlier, and we're using some form of assembly code. Remember that in assembly language we use load. You're loading registers. In this case, we're loading a floating point register. That's the first statements that you have here. So you have your load F. You're loading this into a general purpose register called R2. Now, why are you loading that? Is because you want to multiply the content of what you have in R2 with 60. Now you put this symbol to show that it's actually a number. So you're multiplying this. This is not a register. You're multiplying a content to that register, and you're storing, remember in assembly language, whatever we have on the left-hand side, we always store on what we have, whatever we have on the right-hand side, we store on what we have on the left-hand side. So you're storing the product of R2, the content of R2, which is actually ID3, you're multiplying that with 60, and you're storing that in the register R2. Now you're loading that into the R1 register. Why are you doing that? Because you want to be able to add the content of the R1 register to the content of the R2 register, and then you have your final result, being stored there. So that's simply, what code generation is. Now, don't forget that in all of these processes that we're going through, we have a symbol table representation. And the symbol table is simply a data structure that contains a record of every variable name, not just variable, every name that we're using, whether we're using it in a function, we're using it in a procedure, if you're dealing with older programming languages like your Pascal programming language, okay? Whatever it is that you're dealing with, you want to have a representation of all of these variables in the symbol table. You want to know their name, you want to know their type, you want to know their scope. Now, if you're dealing with functions, for instance, you want to be able to know the number of arguments in that function, you want to be able to know the return type of that function, and you want to be able to store all of this in your symbol table for reference purposes. So on this slide, we show, a representation or relationship between your parse tree and your symbol table. So we're representing what we have here, showing the scope, showing how all of this is going to find expression in your symbol table. Now, this slide, it's like a bird's eye view of all of the processes that we've been dealing with. Beautiful. So we have a symbol table. Remember that everything that we have that is defined as a variable, it's an integer, whatever it is represented on the symbol table. So we have our position, here represented. We have initial represented. We have rates represented here on the symbol table. And we walk through all of the phases from the lexical analysis to syntax analysis, where we have, your parse tree, and then where we have the annotated parse tree. Remember this into float, we're showing that this is going to be converted into a floating point, and that is shown on that parse tree. And then we have our intermediate code generation. Remember our 3 address code, that's what we're using here. And then we have to optimize this code further, and then we have to generate this code. And of course, remember that I mentioned earlier that when you're building compilers practically, you have to figure out what you want to be, at the front end and what you want to be at the back end. So that is shown here the front end and at the back end. And don't forget that there are several cousins, of compilers. We have our preprocessors, we have our assemblers, we have our loaders and linkers, and we have our debuggers. And all of these are several variants of compilation. It was so much fun going through all of this with you. We saw, the different aspects or the different parts of the compilation process. And then we saw all of this in details, we walked them through with practical examples. And in the next series of lectures, we're going to go into these detailed phases of compilation. It's so much fun having you here. We're asking you to please, subscribe, to please share, to please hit your notification button, and to please like these videos. I pray that, this would help us in our course of study. Thank you so much, and God bless you.